And believe it or not, we've touched on a number of these things already. So again, I'll say nuclear medicine in an hour. A little bit of a whirlwind tour, but hopefully we've talked about some of these things enough. Remember in that first lecture we talked about the four forces, right? Gravity, the electromagnetic force, the strong force, the thing that kind of holds the fundamental particles together, and the weak force I said was important in beta decay, and we're going to talk a little bit about beta decay. It's not going to be necessarily that we understand the weak force, but it is what plays a role in that nuclear phenomenon such as beta decay there. Here's our atom. We talked about it quite a bit when we talked about X-ray imaging. Now we're going to talk about nuclear medicine imaging, which in large part, some of what we're going to image with originates from the nucleus of the atom rather than from the electron shell. And that's not completely true. There are certain things we're going to image with where we're not actually using the gamma rays that are produced to do the imaging, and we'll make a specific example of some of those things. I show this again, reminding you of the rest mass energy of the electron. If we converted all of the electron's energy, all of its mass to energy, we'd get 511 keV. We're going to see that number pop up, of course, when we talk about positron emission tomography, where we're going to take the positron, which is the antimatter equivalent of the electron. It has a positive charge but the same mass, and it's going to annihilate with an electron, and we're going to convert both of their masses into pure energy, and we're going to get two 511 keV photons that we're going to then use to image. So let's talk about some nuclear structure and get some terms correct first. We're going to talk a little bit about isotopes. So these are atoms with the same number of protons, right? So they're all going to be, let's say, oxygen atoms. They're just going to have varying numbers of neutrons, but all have the same number of protons. And of course they're all oxygen atoms because it's the number of protons that defines what element the atom is, okay? We're going to talk a little bit about isotones, which are atoms that have the same number of neutrons, and it turns out that we can utilize some of these to create some of the radioactive elements that we're going to utilize in imaging. There's also a concept called isobars. These are atoms that have the same atomic mass number. So if you add up the number of protons plus the number of neutrons, those are the same. The term isomer, which is the excited nuclear state of an atom, and we're going to talk about that when we talk about isomeric transition and the gamma ray that's given off from that. And I want to distinguish all those names from the ion, right, which is the atom that has more or less electrons than protons, and therefore either has a positive charge, a net positive charge, or a net negative charge. So here's oxygen. Right, all atoms with 8 protons are oxygen atoms, and oxygen can have a variable number of neutrons. The most abundant oxygen isotope is O16, 8 protons, 8 neutrons, and in fact 99.762% of all naturally occurring oxygen occurs in that form. There's O17 and O18, by the way. Both of these are stable. They don't undergo radioactive decay. And a very small percentage of the natural occurring oxygen is in those two forms. So this form with 8 protons and 9 neutrons, O18, 8 protons and 10 neutrons. As a matter of fact, you can use O18 to make F18 if you want, that we're going to use to image in PET. And I guess all you need to go out, and there's plenty of seawater out there, right? And 0.2% of it is going to be in the form that we would need to do that. Here's fluorine. Fluorine has 9 protons. It turns out that there's only one stable isotope of fluorine, and that's F19. Notice this is the first element that has an excess of neutrons to protons. Up until this point, with the exception of hydrogen, which only has a proton in its nucleus, right? Helium, 2 protons, 2 neutrons. As we go up, 3 and 3, 4 and 4, 5 and 5. Carbon, 6 and 6, nitrogen, 7 and 7. We just did oxygen, 8 and 8. And here we are at fluorine, where we've got 10 neutrons to go with the 9 protons. And I'm going to make a point of this excess of neutrons in a second. F18 we're familiar with. It's that radioactive isotope used in PET. And of course, F18 and O18, right, they're isobars of each other because they both have the sum of their protons plus their neutrons are the same. So here are isotopes. O16, O17, and O18 are all isotopes. They have the same number of protons. O18 and F19 are isotones. This has 10 neutrons, and this has 10 neutrons. And O18 and F18 are isobars, the same atomic mass number. So here's a picture from an older version of Huda and Sloan's book, and I'm going to adapt it a little bit as we talk a little bit. So as we take a look at all of the nuclei that are out there, we'll notice that there's a certain ratio of their protons to neutrons that occurs. But let's first kind of mark the things that we just talked about. So these vertically oriented lines are the isotopes, the things that have a constant number of protons are vertically oriented lines. And I've drawn in here at about the level of 8 protons, the line that corresponds to where the isotopes of oxygen would fall. Here are the isotones, the things that have the same number of neutrons, and of course these would have variable numbers of protons. So there's O18, F19, the things we talked about. And of course on this line are the isobars, things that have the sum of the protons plus the neutrons being the same. This graph shows, I've drawn some of the different atoms on this, some of the elements. Here's oxygen, O16 here. Here's molybdenum, the 42nd element. It's got 42 protons. And here's tungsten. We've met tungsten before with its 74 protons. You know, it turns out, as we've already mentioned, oxygen has 3 stable isotopes. Molybdenum has 6 stable isotopes, and tungsten has 3. So this notion that there's this simple curve of stable nuclides is really an incorrect one. This is really a better picture of how things look. The black dots on this picture correspond to the stable isotopes. And the things above that black line in blue, you notice these are the things that decay by beta minus decay. And the orange things are the things that decay by beta plus decay, and we'll talk about what that is in a little bit. And the things that are colored yellow here are things that decay by alpha decay that we'll look at. And then down here there's a few other things that I'm not really going to get into in terms of some decay scheme. But take a look at some of the things here. For instance, here at 82, look at how many, as we go across, right, things are stable that have various numbers of protons but have a fixed number of neutrons there at 82. There's a number of stable isotones there with 82 neutrons. And here is the list of them. Here are those 5 things, all of which have 82 neutrons that are stable. Then also, if you look right here, notice how many dark black lines there are here right at this 50 level, right? Those are all the stable isotopes containing 50 protons. Notice how many of them there are. It turns out that that's 10. Tin has 10 stable isotopes, by far the most here. So it's not as simple as a single curve with 1 at each point that does that. But there's a general trend here. Does everyone see that general trend? Right, this line, this dark line, is the line at which the number of protons and the number of neutrons would be equal to each other. So does everyone see that as the number of protons in an atom gets bigger, it turns out that you have to have a relative excess in the number of neutrons in order to have nuclear stability there, right? And that's helpful to us in that we can sort of predict a little bit as what the decay scheme might be by knowing whether you exist up in this blue region, right? You have more neutrons than you need. You have an excess of neutrons. Or if you're down in this region, where I guess you would say you have either a relative paucity of neutrons or perhaps too many protons. And that's going to help us decide what the decay scheme is going to be there. So going back to that picture, right, these are the things that have too few neutrons, or if you will, have too many protons relative to neutrons. And these are the things that have too many neutrons, or if you will, have too few protons relative to the neutrons there. Here's that nuclear binding energy we talked about, right? The most stable things sitting in this range. And so things up in this range are really going to decay into that region to try and make things become more stable. So by way of review, right, nuclei with different numbers of protons or neutrons are called nuclides. Unstable nuclei are called radionuclides, not radionucleotides. We're not studying RNA or DNA. Atoms with unstable nuclei are called radioisotopes. So here are some of the hydrogen isotopes, right? The deuterium, tritium, there. So unstable nuclei become stable via radioactive decay. That decay may give off energy in the electromagnetic spectrum, pure energy, gamma ray photons, or it may give off particles, or frankly, some things decay using both schemes. The four processes are isomeric transition, alpha decay, beta decay, and gamma decay, and I'm going to go through those here in a second. Isomeric transition, alpha, beta, gamma, electron capture, actually, I should have here. So the parent radionuclide decays to a more stable daughter. The combination of energy, mass, and charge has to be conserved in that. So what is radioactivity? Well, activity is the rate of change of the parent into the daughter. So if we have n number of parent atoms at a given times t, it turns out that that rate of change, the change in the parent per unit time, is simply proportional to the number of parent that's present times this constant here. This is the decay constant, which varies depending on the radioisotope. It turns out that this is a simple little differential equation, and the solution to that equation is the decaying exponential, so that exponential decay that we're all familiar with. And once again, we're more familiar with that notion of half-life rather than this decay rate parameter, similar to that linear attenuation coefficient that we had in X-ray imaging. The half-value layer was a little bit more intuitive to us. Here, the half-life is a little bit more intuitive to us. Activity is the number of transformations that occur per unit time, and there are a couple of different units for that activity. The System International unit is the becquerel. It's the 1 transformation per second, and the non-SI unit is the Curie, 3.7 times 10 to the 10th transformations per second. So 1 millicurie equals 37 megabecquerels. And this is one area where we still continue to use the non-SI units. And I jokingly say sometimes that's probably because the patient would rather hear us say that we're going to give them 10 millicuries of something than we're going to give them 370 megabecquerels of something, right? Although those are exactly the same thing. The physical half-life and decay constant lambda are related by that equation that I just had on that previous slide. That decay rate, that activity, equals the number of atoms that we have in the sample times that decay constant. All of these radiopharmaceuticals that we're going to deal with have a biologic half-life as well as their physical half-life. If we just watch them decay in a vial sitting on the counter. And so their true their true effective half-life is really determined by both the biologic half-life and their physical half-life. So how quickly do we eliminate it from our system in addition to how quick it's decaying? And of course, the effective half-life is always going to be less than both the biologic half-life and the physical half-life. And if you want to calculate that, it's fairly straightforward. If you'll multiply those two half-lives together and divide by their sum, that will give you the effective half-life. So something like technetium 99M, which has a half-life, a physical half-life of about 6 hours. And let's assume that the radiopharmaceutical that we've had it chelated it with has a biologic half-life that's also 6 hours. So then if we did 6 times 6, that would be 36. 6 plus 6 is 12. 36 divided by 12 is 3. The effective half-life in the body would be 3 hours. Okay? So let's talk about how some of these decay schemes actually work in radioactive decay. Some atoms have a nuclei that can exist in excited state. And this is not an uncommon thing, but most nuclei that end up in an excited state as part of radioactive decay immediately go back to a ground state, and they don't exist in that metastable state for very long. When they decay to that ground state, they release a gamma ray photon. It comes from the nucleus there as that atom goes from that excited state down to its ground state. Now, radionuclides that can exist in that excited state for a relatively long time, and we're talking about a relatively long time on the atomic scale, so greater than 10 to the minus 12 seconds, are referred to as being metastable. All right? And the most important metastable radionuclide that you should know of that decays via isomeric transition is technetium-99m. As a matter of fact, technetium-99m, the M is for metastable. And clearly technetium-99m, right, it's a real outlier there because this exists in that excited state for quite a bit of time, right? We've talked about the fact that its half-life is around 6 hours. What's nice about isomeric transition? Well, we get decay to that stable state and we get this release of this gamma ray. So that gamma ray is given off. Here we see that happening. That's labeled 1 in this picture here. Sometimes we don't see that gamma ray produced. Sometimes that excess energy in the nucleus gets transferred to one of these orbital electrons, typically a K-shell electron here, and we get what are called these internal conversion electrons, these electrons which are going to head off with kinetic energy that would be equal to what this gamma ray energy would have been minus the binding shell energy of that electron, these internal conversion electrons. Unfortunately, they're going to deposit dose in the patient, right? The negative effect of this here. And once that's gone, of course, the characteristic X-ray production can occur, right? Where this L-shell electron is going to come in and fill that slot and give rise to that characteristic X-ray. Or sometimes this energy difference gets imparted to an outer shell electron and we get the production of those Auger electrons. So things that we've talked about before. But in isomeric transition, the main thing that happens is the rise of this gamma ray here. And as a matter of fact, in technetium-99m, 88% of the decays result in the production of this gamma ray here. Only about 12% of the events result in internal conversion electron. Of course, we'd love it to be 0, right, because that would be less dose in the patient, but about 12% there. So that's what happens in isomeric transition, that type of decay. Beta minus decay. In beta minus decay, a neutron inside the nucleus gets converted to a proton. So right away, remember, this must be occurring in things that have too many neutrons relative to their protons, because to become more stable, one of the neutrons in the nucleus is going to get converted to a proton. And it's going to release an energetic electron in doing that, right? The charge of this neutron is neutral. We need to convert it to a proton. That means we need to lose some negative charge there. So it gives release of this energetic electron, which is referred to as a beta minus particle. It also results in the production of an antineutrino, which I'm not going to go into here. Of course, as I said, this occurs in nuclei with too many neutrons, or if you will, too few protons. And one of the most important examples we should know of this is I-131, right? I-131 is a beta minus emitter. It gives off energetic electrons. And we use this for treatment purposes, right? We talked about the fact that when we talked about the interaction of particulate radiation with matter, that these energetic electrons deposit all their dose locally, right, within a few tenths of a millimeter of where they're created. And so it's great for that treatment. Now, right away, some of you should say to me, well, wait a second, we use this to image as well. I mean, we don't use it just to treat. I've taken images of patients after we've given them a treatment dose to see where that's been taken up. And absolutely, and that brings me to a point I want to make sure I make is right. I'm showing some prototypic examples here, but remember, some of these things decay through multiple decay schemes. So I-131, it turns out, also gives off gamma rays as part of its decay scheme as well. All right, so we know about I-131. So beta plus decay. So in beta plus decay, one of the protons inside the nucleus gives off some of its positive charge and gets converted to a neutron. And it gives off that energetic positron to do that, the beta plus particle, along with a neutrino. And again, I'm not going to get into the neutrino portion. Well, of course, if a proton is going to get converted to a neutron, this must be occurring in nuclei that either, if you want to view it as have too many protons or too few neutrons. All right? Since that positron is the antimatter analog of the electron, it's very quickly going to lose its kinetic energy within a few millimeters of where it's created, and it's going to annihilate with an electron. It's going to come in contact with an electron there, and they're going to annihilate each other, and all of their rest mass is going to be converted into pure energy. And we get the production of two 511 keV coincidence photons. Notice we don't call these gamma rays, right? Because they weren't produced in the nucleus of this atom. They were produced as a result of the positron that was produced in the nucleus of the atom. So 511 keV photons here that are produced. The most important example we should know about this by far is F-18, right? These are the positron emitters that we're going to use in our PET imaging. Okay, so in PET imaging, we're not imaging the positron, we're imaging the annihilation photons that are created as a result of the positron projection. In electron capture, a proton inside that nucleus is going to get converted to a neutron, but instead of giving off positive charge like we saw in beta plus decay, instead it's going to do that by capturing one of the inner shell electrons and bringing it into the nucleus. So electron capture, it's going to bring an electron into the nucleus and convert that proton into a neutron. So again, this is something that occurs in nuclei with too many protons, or if you will, too few neutrons. Immediately you should be asking yourself, well, what the heck are we imaging with here, right? So far the only thing you've described to me is the capture of an inner shell electron into the nucleus. Where's the thing that we're going to use to do some imaging? Well, since we get that electron removed from its inner shell, from that K shell, an L shell electron is then going to fall in place, right, from the L shell down to the K shell, and we're going to get the production of characteristic X-rays. We're going to get characteristic X-ray production. So in electron capture, we're actually imaging with X-rays. We're imaging with characteristic X-rays. And most important, well, this is a little stretch. I guess I could have put gallium-67 up here, right? I could have put thallium-201. We don't do a lot of cardiac thallium imaging. There are a number of others that I could have put on the list here that, rather than the, not as prototypic as some of the others. But this is an example that you should know of, is a better way to put it on this slide. I want to talk a little bit about what exactly we're imaging with, and the reason I left thallium on the list, even though we don't do it quite as much, is I had thallium on my slides to do that as opposed to gallium or some of the others, and so I can make the point I want to make. So what happens here? Here's thallium. Does everyone see it? 81 on our list. I'm going to blow it up a little bit here. Here's thallium. Here's the K shell binding energy. Here's the L shell binding energies for thallium. Thallium, one of the protons in thallium's nucleus, is going to capture an electron and bring it in and get converted to a neutron. When that occurs, what does thallium become? Does everyone see that thallium now has one less proton in its nucleus, and it becomes an atom of mercury? Okay, it becomes an atom of mercury. And so it's the characteristic X-rays of mercury that we end up imaging with when we image with thallium-201, the characteristic X-rays of mercury. And we can calculate roughly what those are, right? We can take this 83 and subtract off this 14, so 83 keV minus 14, 15 keV. So we're kind of in the 68 kind of keV range there. And notice, depending upon whether it's the L1 or the L2 or the L3, we get, or the M shell, we get some varying range of values for that. So we've got these multiple little characteristic peaks that we're imaging with. So I want you to understand electron capture. I want you to understand that when we capture an electron into the nucleus, it reduces the number of protons in the nucleus by 1, so it's actually a different atom, and that what we're imaging with is actually the characteristic X-rays of that new atom. Well, the last one I want to mention is not one that we're really that interested in terms of nuclear medicine imaging, and that's alpha decay, where we get these alpha particles emitted as some of these larger, quite unstable radioactive elements decay to more stable forms. It really only occurs in nuclei with fairly high atomic number. Most important examples we should know of are probably radon, right? As the radon decay, we mentioned that they give rise to these alpha particles. They're very energetic, but fortunately they can't travel very far due to the fact that they're quite massive and have quite a bit of charge. So there's a little summary of the decay schemes as we've talked about them there. I just put this picture up to remind people once again, right? Alpha particles really can't even travel through a piece of paper, but we worry about them because when they're floating around in the air, you can still end up inhaling them and causing quite a bit of damage to the inner linings of the lung there. Beta, a little bit more penetrance, but remember, the electrons still have some mass and some charge, and therefore it's stopped fairly readily. And of course, the X-ray or the gamma ray can have quite a bit penetrating power. As a matter of fact, since it has no mass and has no charge, you can certainly make ones that are energetic enough to make it through quite a bit of lead. All right, so let's talk a little bit about now that we've talked about decay schemes, talk about radiopharmaceuticals, how we do some of our planar imaging, tomography, a little quality control, and some maybe dosimetry towards the end, just a little bit. You may see these decay scheme diagrams, and I show one of these just in its general form once again, because I want to remind you that sometimes you'll see that some of these radionuclides will decay via more than one scheme. So maybe by isomeric transition scheme and by giving off a gamma ray, and also by giving rise to a beta particle, let's say. How do we produce them? Well, there are a lot of different ways. Some of the radionuclides can be produced via fission. Molybdenum-99, which we then use as a generator for technetium-99, M, is produced that way. So most of the molybdenum we get comes from nuclear power plants. We can produce them via neutron bombardment, and P32, I-125 are produced this way. These guys all have excess neutrons, and then therefore they tend to undergo beta minus decay. We can also produce them via cyclotron by bombarding atoms with protons, deuterons, alpha particles, thallium-201, gallium, indium is another nice example. Fluorine, F18 can be produced that way. And since these have excess protons, they tend to either decay by positron emission or by electron capture. Okay? In general, some of the smaller ones tend to undergo a little bit more positron emission, some of the larger ones a bit more electron capture. That's just kind of a general rule of thumb. Radionuclides can also be produced in a generator, and that's how we get most of our technetium-99M. We get molybdenum-99, and as it decays to this. And so those Technetium 99M generators are a nice way to get that. And I'm going to talk about that in a little bit more detail when I talk about technetium. And these products can really end up decaying the parent to produce the daughter through a generator type phenomenon by any one of the ways that we just described. And here's a nice summary of what we just talked about in the production of some of these from a table in Bushberg's book on medical imaging. So remember, radiopharmaceuticals. We now have this radioactive atom, but in nuclear medicine, we're really trying to image physiology, right? Not just anatomy that we're doing in some of the X-ray imaging we looked at. So we have to take this radioactive atom, this radionuclide that we've created, and we have to make a radiopharmaceutical from it. In other words, we have to do chemistry with it to get it to be part of some biologically active drug, if you will. And I show the periodic table. We know how a lot of these things behave, but take a look at some of these things like technetium, right? I mean, some of these are pretty good-sized metals. So how do you chelate them to some other compound and still have it maintain its biologic activity? And the radiochemistry involved with doing that is a whole field into and of itself. So really, what would be the ideal characteristics for us in terms of a radiopharmaceutical? Well, we'd really love to have something that has a relatively short half-life, right? That way, if it stayed in the body, it would decay fairly quickly and we wouldn't end up with a long-term exposure to that person and people around them. But we don't want it too short. I mean, if the half-life is a matter of seconds, how do we get our imaging done that we want to get done? We really would love monochromatic gamma ray production, right? And we'd love the energy of those gamma rays to be sufficient enough that they escape the body, right? That the body doesn't absorb them all because they're such low energy and the dose is just all deposited in the body. But we'd like the energy to be low enough that we can actually do a decent job stopping them with our camera or our detector. We'd love them to have minimal production of particulate radiation, such as those beta particles, or in creation of those internal conversion or OJ electrons. And we'd love for that radiopharmaceutical to localize itself at that organ of interest, be relatively non-toxic, have high radionuclide, radiochemical, and chemical purity. And of course, we'd love it to be inexpensive and readily available. Boy, that's a pipe dream, right? But those are the properties we'd love to have. The localization of those radiopharmaceuticals, well, there are many different ones that we have, and I just jotted down some of those, right? Sometimes we're looking at compartmental localization, like in a GI bleeding study, where we're just going to label red blood cells and see whether they stay in the bloodstream as opposed to dumping into the gastrointestinal tract. Sometimes we're just imaging simple exchange or diffusion, and this is true in radionuclide bone scanning with MDP, where we're really looking at exchange of that with the bone, or in ventilation imaging with labeled gas. Sometimes we're imaging phagocytosis with sulfur colloid, or capillary blockade when we're imaging using labeled microaggregated albumin. Or cell sequestration, or frankly, metabolism when we're imaging with some of the glucose analogs, like in F18 FDG PET imaging. Technetium 99M as a radionuclide comes really close to some of the properties that we talked about. And that's why you see it used in various labeled forms to perform greater than 80% of the non-PET nuclear studies. It decays with 88% of its nuclear transformation, resulting in the emission of 140 keV, about 140.5, 141 keV photon, which is great, right? That's ideal, escapes the body like we talked about, still low enough that we can stop it fairly readily. Unfortunately, the remaining 12% results in these energetic electrons and deposits dose in the patient, but that's a relatively small amount. And for that reason, there's been a lot of chemistry developed around technetium. The other thing that's nice about technetium is we can really get technetium fairly readily using a molybdenum generator. So here's alumina absorbed with molybdenum, and as it decays, some of that decays to technetium, it becomes water soluble in that. And so here's a sterilized solution of saline connected through that column via this tubing. And if you popped an evacuated vial onto the little needle, if you will, on the top of this, it would suck that fluid past that column, taking off the soluble technetium, and you'd end up with technetium in your vial, and hopefully it was working well, and you ended up with very minimal amount of breakthrough of molybdenum in your vial there. How many people still get a technetium generator like this delivered to their hospital here? So there's some, you know, more and more it's becoming, doses are becoming available if you especially live in a fairly well-populated metropolitan area where you can have your technetium delivered to you on a per dose basis. You tell them what time your study is going to occur, they will send you the unit dose that you need such that at that time it would have decayed to exactly what you needed it to be. But some places still have their generator that they use each day. And if you have the generator, one of the things that you know that's really nice about it is if you start off with no technetium and just your molybdenum, and you watch after about a 24-hour period, you reach a peak in the amount of technetium that's available there. So you can take all the technetium from the generator and then let the next 24-hour period go on where, again, that amount of technetium was going to rise over time as that molybdenum decays until it's time to elute the generator once again. So it's really nice to set up. The ratio of half-lives between molybdenum and technetium are such that you end up in this transient equilibrium that reaches its maximum right around 24 hours, which is really convenient for what we do, where each morning we'd want to elute the generator and start our imaging for the day, if you will. I already mentioned that the fact that in nuclear medicine we're really trying to image physiology, right? And so that a lot of radiopharmaceuticals have been designed for that purpose. And if you go back, 20, 30 years ago, you had a lot of people doing radiochemistry in your nuclear medicine department to try and prepare things for you. And more those have been converted to commercial kits where you take that pertechnetate, that technetium that you've eluted from the generator, and you inject it into a vial using a syringe, and you do minimal things to either agitate that or heat it or just process it to get your radiopharmaceutical there. And that minimizes the need to really perform chemistry with radioactive materials in the nuclear medicine department. So for instance, here's one of the MAG3, one of the renal scan agents, right? And basically you just pop this vial out, top off, and inject the appropriate amount of pertechnetate in that to have that occur. So we've talked a little bit now about how radioactive decay occurs, what some of the ideal things that we'd like to see in terms of imaging agents are, but now how are we going to stop that radioactivity? And I'm going to make an analogy between the planar nuclear medicine imaging camera and screen film or digital imaging that we talked about. Because really the collimator is kind of analogous to the grid that we talked about, if you will. And that sodium iodide crystal that we're going to use in planar nuclear imaging is kind of analogous to that intensifying screen or that input phosphor that we were talking about in CR type imaging. And the photomultiplier tubes and the detection electronics are analogous to the film or to the digital detectors that we're using in digital radiography. The major differences is that the detector in nuclear medicine also measures the time and the energy of each event that was occurred, not just where it happened on the imaging detector. And ideally, that imaging is performed from unscattered gamma ray photons. We've talked about some of the others are not gamma rays, but that undergo photoelectric absorption in that sodium iodide crystal. And that shouldn't surprise us again, right? How does the crystal stop it? It interacts just like electromagnetic radiation interacts with any tissue. So here's that gamma camera. On the front, we have this collimator, and I've made the analogy to the grid. Right? the difference here is, how do we get an image in focus in radiographic imaging? Well, we use a point source of radiation. The radiation all comes from the point source in the X-ray tube, and so therefore the image is in focus. When we give a radionuclide, a radiopharmaceutical to a patient, we end up with a distributed source of radiation. And so we really need to make sure that we only detect gamma rays traveling in a particular direction. Otherwise, our image is just going to be this absolute blur of activity traveling in all different directions. Okay, so it's really the collimator that, if you will, acts as the lens to focus the radiation so that we're only accepting it along a particular direction. Beneath that is our sodium iodide crystal. So when one of these gamma rays interacts in the crystal, we're going to get the production of lower energy visible light, which is going to be readily detected by our photomultiplier tubes. Unlike our X-ray imaging, we're going to have really tiny small detector elements because we need this really high resolution imaging that's going to occur as I really flood the patient with X-rays in a very short period of time. Here I'm going to image a longer period of time. And when these events occur, they're going to occur far enough in space and time relative to each other that I can detect each one individually. And by detecting the amount of light that is seen by some of the adjacent photomultiplier tubes, for instance, this tube here is going to see the majority of the light from this event. The one here, a smaller percentage of that. I can actually interpolate where the event occurred by knowing how much light is detected by the few surrounding tubes that detected it from that. And the amount of light that they detect, the sum of the light that they all detect, is going to allow me to know the energy of the interaction that occurred. So I'm going to keep the time information, the position information, as well as the energy information in nuclear medicine imaging. Here's that photomultiplier tube that's going to detect that event when we do that. So I've already talked a little bit about it, right? They consist of that scintillation crystal, the photomultiplier tube, and the electronics with that collimator mounted in front. The crystal is typically about a 3/8 inch piece of sodium iodide doped with a little bit of thallium. This scintillator needs to have good stopping power for the photons that we want to image, and it needs to be very fast because I want to record the event that occurred and immediately be able to record the next event. If it's slow, then multiple events are going to pile up on each other, and it's going to be hard for me to distinguish the individual events. That light emitted is detected by those PMTs, and the electronics are going to calculate that location as I talked about. And a typical nuclear medicine image contains about 500,000 to, oops, I missed a zero here, about 1 million counts, okay? So there's that picture once again. We've got those. And you've all been in the room while the imaging is going on. On the scope that's up there, it's showing the individual events that have occurred over the last, say 5-second interval or so. Let's just take a look at that sodium iodide crystal and its efficiency for stopping gamma rays of particular energy. So here are some different energies of gamma rays. I put down 100, 140, this is technetium. And let's just say we were working with photons that had energy up in the range of 511 like we have in PET. So here's a 1/4 inch thick, here's the 3/8 inch thickness we have. That's the standard thickness in a gamma camera. And I've gone out to be a little thicker here. So notice that for 140.5 keV, that 3/8 inch thickness stops about 90% of those gamma rays from technetium 99M, which is very nice. Just like we talked about with our screens, right? The thicker we make this crystal, the more room we have for light to diffuse, and the worse our resolution properties are going to be. So we don't want to make the crystal thick just because it has greater stopping power. So this 3/8 of an inch thick is a nice balance between resolution properties, but still stopping the majority of the technetium 99M. The reason I included 511 keV photons here was I want you to realize right away that this is not the right material for doing positron emission detection, right? We're only going to stop 5% of those, and wait a second, we want to stop the pair, not just one of them, so the chance that we stop the pair is going to be exceedingly small. So we're going to actually use a different type of scintillator for PET imaging. Even going out to a 1-inch thickness, notice that only goes up to 14%. We do this pulse height analysis. Remember what I was telling you, that if you look at the total amount of light that is taken, that's the height of the pulse there. It's going to allow you to discern where the energy was of the gamma ray that was detected. And typically we accept so that we, a window so that we accept any events that are detected by the detector that fall within a certain window of the peak. Because let's be honest, when a 140 keV gamma ray photon from technetium strikes the crystal, it doesn't always produce exactly the same amount of light. There's going to be some slight variation. So we're going to open up a little window called the photopeak window, and typically it's about 28%. So if we're at 140 keV, we'll look 10% below that, right, which would be down to 126, and 10% above that, which would be up to about 144. Any pulses that occur whose energy is estimated to be in that range, we're going to accept and make our image from. A wider window would accept more photons, so it would decrease our noise. But unfortunately, you know, what are some of these things that have lower energy going to be? Where they're going to be gamma rays that have scattered in the patient. And so we don't really want to accept those. They're just going to degrade the quality of our image. By the way, certain radionuclides, like gallium-67, have more than one photopeak. They give off gamma rays of multiple different energies, and we actually set up multiple ranges in which we'll accept them. Not one big wide one that accepts all, but multiple narrow ranges centered right at where the peaks are. So here's what happens if I start to detect gamma rays coming from a patient who's been given technetium 99M. I'll see if I start to count the detected events in the crystals, I'll see this big peak here at 140, centered at 140. And there's that window where we're accepting these events. All these events in yellow that are occurring, we're accepting, saying, yes, those are true events that I want to use to make my image. Notice beneath that where some of these scattered events are, you still have some little bits of peaks. And I want to mention what some of them are from, just really a couple of things here. Notice there's one right down here just below 80. And does anyone know what that peak is from? What's that peak from? Yeah, that's scatter within the collimator. That happens to correspond to the characteristic X-ray energies of lead, and our collimator is made of lead. So when events interact in the lead collimator and we get some characteristic X-ray production, and we certainly don't want to include those in making our image. It's not shown here because the picture would have to be up at 280 keV, which would be up this way, but usually there's a little tiny peak situated up at 280 keV. And what's that from? Those are coincidence events where a pair of events happen to occur near simultaneously in close to the same position in the crystal. And so they can't be discerned temporally. They can't be discerned in time because they happen too close together in time. So our pulse height analyzer thinks for some reason something with 280 keV just struck the detector. Completely artifactual there, but that's one of the other things we might see. Moving right along, we'll talk a little bit about those collimators. I've mentioned the analogy to the grid. They're typically made from lead, and they have thousands of holes in them through which the gamma rays can pass. I mentioned that they're mounted in front of that crystal, and they really act like a lens to only accept gamma rays coming from a particular direction. And there's a number of different collimator designs, each providing some trade-offs between resolution, noise, and field of view. So here's a nice parallel hole collimator. It's only going to accept gamma rays that are traveling parallel to each other. Here's a pinhole collimator. It's going to do kind of the same thing that imaging and X-ray imaging does, where all of our X-rays emit from a single point source, the focal spot on the X-ray tube. Here we're just going to insist that all the X-rays we obtain travel through, or so the gamma rays we obtain travel through a single pinhole camera to form our image. Here's a converging hole collimator. Notice it has a very similar behavior to the pinhole, the only difference being that the object doesn't get flipped, and you can image closer to the object than you can for a pinhole collimator. And here's a diverging hole collimator, where we actually get this spreading out. The holes in the collimator actually look at a larger field of view. So what kind of things do we image with this? Well, a lot of imaging in nuclear medicine is done with a parallel hole collimator. We used to do some thyroid imaging with the pinhole collimator, where you really were looking at a small object and wanted to magnify the field of view. You know, where you have a fairly small camera. So we used to have a portable nuclear medicine camera that we sent up to the intensive care units to do portable VQ scans. So there the camera was relatively small, but we needed to see the large field of view, the chest. And so the collimator on there was a diverging hole collimator, which took that large field of view and really brought it down to the size on the face of the camera there. We talked about the fact that the collimator is made out of lead, and oftentimes it's made out of these almost corrugated pieces of lead that, when they're stacked together, form these hexagonal holes, if you will. Of course, the higher energy some of these radionuclides are. Here's I-131, which, yes, is a beta emitter, but also decays through the production of some high-energy gamma rays, and they will frankly pass right through the thin lead septa of some collimators. And so you get this septal artifact, where this is passing through the walls of some of these septa, and that star pattern corresponds to the orientation of the walls in that collimator. You'll see that here. Okay. The performance of the collimator is measured in terms of its resolution and efficiency. And resolution we measure just like we did in the other ways. We can have some bar phantoms. We can try to calculate a modulation transfer function. Or we can image a point source or a line source and see how much that gets blurred out, that full width, that half maximum that some of you may have heard of. The sensitivity refers to the fraction of gamma rays that pass through the holes of collimator. In most general purpose collimators, less than 1 in 10,000 gamma rays that exit the patient actually make it through the holes of the collimator. So the same sort of inefficiency that we talked about with X-ray imaging, right? Where only 1 in 1,000 X-rays made it through the side of the patient. There's an awful lot of gamma rays here that we're actually not utilizing to make our image. Increasing the length of the holes in that collimator, right, is going to improve the resolution properties, but unfortunately it's going to make the sensitivity worse, just like when we talked about the grid. In addition to the collimator types, the parallel hole, the converging hole that I showed you, the pinhole, they also tend to be classified based on their resolution, sensitivity, and energy characteristics. And some common types are high sensitivity, high resolution, low energy, medium energy, high energy. And I'm going to talk about some of those in a little bit. The one thing I want you to realize too is that the further you get from the nuclear medicine gamma camera, the poorer your resolution becomes. Okay, so if you think about it, look at the area that this particular hole in the collimator samples. Notice the further away you get, the wider that it becomes, that wider the field of view that it sees becomes. And that's really what's determining the resolution at a particular depth. So it's very important in nuclear medicine to get the object that you're interested in imaging as close as possible to the gamma camera to keep your resolution properties as high as possible. Okay. So what are high sensitivity cameras? Well, they're ones that allow to collect as much as possible of the radiation. They tend to have short, wide holes with relatively thin septa. High resolution collimators have long, thin holes. Low energy collimators, right? If you're going to image things that have relatively low energy gamma rays, the lead septa don't need to be nearly as thick. You don't have to worry as much about the high energy gamma rays that might penetrate through those septa. And the high energy ones, of course, have very thick septa. We've seen these images obtained on a persistent screen during the examination. You can see it can be accumulating the detected events on the camera over the previous 5 seconds and update as time goes on. And after acquisition, we can often frame those. You can take the events that were acquired every 5 seconds and make that a frame in the next 5 seconds. And we can play that cine clip to see how the distribution is changing there over time. Nuclear medicine images are typically much lower resolution, maybe a 128 by 128 matrix, quite a bit lower than we had in CT, and certainly much lower than in plain film imaging. And usually we acquire them for a specified number of counts or a specified amount of time. And we can do a lot of post-processing since we save that temporal information, right? We've got that time information as well, so we can calculate ejection fraction, cardiac output, right? A renal split function, all those kind of things, really imaging that physiology. Let's talk a little bit about single photon emission computed tomography. Again, another tomographic technique, only here, rather than make a map of the attenuation values, like in CT that we talked about earlier today, here I'm going to make a map of the distribution of the radio tracer, right? But we're going to do it a very similar way, the same filtered back projection techniques. I'm going to acquire these projections and use filtered back projection to reconstruct that image. But what are the differences? Well, typically we rotate that gamma camera 180 or 360 degrees around the patient. We usually only obtain something in the neighborhood of 64 or 128 projections. So we don't sample every degree as we rotate around. And the matrix, the number of detectors in a single line is not the 750, if you will. It's closer to 128. But we are acquiring in both dimensions. We are using a planar detector, not a single row of detectors or a thin strip of 64 rows of detectors, if you will. The reconstructions are performed either filtered back projection or iterative, and we've used iterative techniques in nuclear medicine for a much longer time than we have in CT. And the main reason for that is because we don't do it on quite as large a matrix, it isn't computationally as demanding as doing it on a 512 by 512 matrix. So that iterative techniques really allows us to do some better noise handling, do some attenuation correction, some scatter correction to improve the quality of the image. So there's that gamma camera rotating around the patient like we've talked about. You know, multi-head cameras allow faster acquisitions because you're basically acquiring 2 or 3 of your projections simultaneously. We really want to choose an orbit that keeps the gamma camera as close as possible to the object of interest. So if we rotate 180 degrees for a cardiac imaging study, since the heart is located on the left side and more anteriorly than posteriorly, we really choose an orbit that starts and keeps the gamma camera closest to the heart in that location, rather than the one that's operating posteriorly and on the right that would be farther away from the heart. Spatial, just like in CT, the spatial resolution is lower than it is in planar X-ray imaging. The resolution in SPECT imaging is poorer than in planar nuclear medicine imaging. But we have better contrast resolution. We no longer have the radioactivity in 3 dimensions only projected into a 2D plane. We have its 3D distribution there, so we get better contrast resolution. Noise is a major factor in terms of limiting the quality of nuclear medicine images. But because we have such good contrast resolution there, right, that's really the benefit to us, right? Yes, the images may be noisy, but they have fabulous contrast, okay? So the benefit of SPECT is that improved contrast owing to that tomographic technique. And I don't know if you know, some of these cameras are dual head cameras. There's some older 3-head cameras that are out there that were utilized. Let's move on to talk a little bit about positron emission tomography. It uses positron emitters, almost exclusively F-18, but there are a few others out there. And here we're going to image the two 511 keV annihilation photons that are created. Those annihilation photons basically travel at 180 degrees from each other in a straight line. Not quite true because of the little bit of kinetic energy that positron had, but very, very close to being true. So we really don't need to use any collimation, right? If we can just detect the two events, we know that they were traveling along the same line. So there's no need to use collimation because we've already know the path along which that event was moving. However, collimators can be used in PET, and they were used early on, and basically they were used to minimize the number of events that occurred simultaneously so that you didn't get these false pairs of coincidence by multiple events occurring at near instantaneously in time. As our electronics have gotten faster and better, the need to have collimators in PET has decreased. So we're going to use, remember we talked about how sodium iodine really doesn't do a great job. So the detector crystals in PET tend to be things that have higher Z, bismuth, germanium oxide, LSO, GSO. So here's PET, right? Here we have that positron emitted. It ends up finding its way with an electron and the annihilation event occurs. And if I can detect this event here and this event here near simultaneously in time, I know that the place at which that event must have been emitted was along that line. Now, if I had timing electronics which were precise enough to tell me the exact time at which this occurred and the exact time at which this occurred, I could actually figure out the exact location on which this line on which they occurred, right? If they were detected at exactly the same instant in time, the event must have occurred at the location so that this distance is equal to this distance, right? And actually that timing is now coming more and more into play in terms of improving the quality of our PET scanners. But realize how difficult that task is. These are traveling at the speed of light. The speed of light is 1 meter per nanosecond. I have to get the timing of those events right down to the level of the 1,000th of a nanosecond if I want to know that event to within a millimeter of accuracy. Okay, that's a very challenging problem. But I think we'll see it incorporated in PET CT scanners in the next 5 to 10 years. Remember I mentioned that in the old PET scanners you would see collimators in there, and they were really in place so that you restricted to only be detecting events that were traveling in this direction and not so much detect events in this direction. In other words, we operated the old PET scanners in 2D mode where they were detecting, if you will, events occurring in a single slice and not allowing 3D detection of events. That has really kind of changed. Both SPECT CT and PET CT incorporate the tomography of nuclear medicine with the tomography of X-ray imaging. And they do that by combining these units together, and it allows us to really precisely anatomically locate these areas of increased radiopharmaceutical concentration. If you think about it, the ideal PET or nuclear medicine radiopharmaceutical accumulates at the area of abnormality and nowhere else. So in some sense, you would get a picture of a bright spot and that's it. And it's really nice to be able to overlay that on the anatomy, the anatomic imaging. And so SPECT CT and PET CT have really become the norm. In addition, that CT data set, right, that's a measure of attenuation maps. And that CT data set can be used to correct the attenuation that occurs in PET imaging, right? So as gamma rays try to escape from the body, some of them are attenuated. If we know the map of attenuation of the body, let's say from a CT scan, we can correct for that. The correction is complex because the CT scan was acquired at energies that are around the 140 or lower range. And we need to correct for annihilation photons that may be up in the 511 keV range. So the attenuation map needs to be adjusted for the appropriate energy. We talked about that generator. The generator, if that generator is damaged, some alumina can break through, some of that molybdenum can break through. That'll interfere with the kit preparation, but more importantly, molybdenum 99 emits 740 and 780 keV photons. And so we really want to check for those injuries to make sure our generator is functioning properly. We want to see very little breakthrough through there. We always want to check our radiochemical purity, and I won't read these to you. The radionuclide purity, radiochemical purity, the chemical purity, certainly want to make sure our radiopharmaceuticals sterile as well. We do some quality control with our gamma camera. We want to make sure that we're photopeak correctly by using a small sample of a known source like technetium. We do a uniformity with a flood source. We do that with the collimator in place. That's an intrinsic, without the collimator in place is an intrinsic flood. With it in place, an extrinsic flood. We can check our resolution and our linearity using a Bohr phantom like this. We want to do our dose calibrator check. It's an ionization chamber we're going to use to make sure we check our doses and their appropriate amount before we give them to the patient. There's a check for constancy that we do using two very long half-life sources like cobalt-57 and cesium-137. We're going to check annually the accuracy with a calibrated source to see that it measures correctly. We're going to check our linearity by looking at a sample of technetium-99. We know the half-life of that, so we know that as we measure it repeatedly over 72 hours, it should measure appropriate values along the course. I mentioned spatial resolution. Both the collimator and the detector play a role in here. I'm not going to go into that slide anymore. I mentioned the fact that nuclear medicine images have extremely high contrast. That's why we utilize them. There's also quite a bit of noise there. We can improve that noise by getting more counts, but realize that means either a longer imaging time or a higher dose to the patient. So we really want to find that appropriate balance between the contrast we need and the noise that we will accept. There are many number of artifacts that we'll see in nuclear medicine. Damaged collimators end up, because you typically fold over the septa in the lead, end up looking like cold spots on the image. Patient motion, I think most of you have seen an example where it looks like the patient has two heads because they've changed the direction they were looking halfway through the scan. Metal worn at the patient attenuates, the gamma rays escaping them. I've got an example there. Photomultiplier tube failures look like a cold spot. An off-peak image depends on where the peak was set, but if you set it down too low, you just get this very kind of scatter-looking image that's barely perceptible outline of the anatomy you're looking at. If you set it too high, you may not get much of anything in the image. And if you've got a cracked crystal, that looks very similar to the damaged collimator, but of course if you do a flood with the collimator in place and you do a flood with the collimator off, you'll quickly be able to determine which one of those two things are going on. Here's a patient with their cross right on their necklace, right, that metal attenuating there. Here's a nice cracked collimator. You see it as an artifact. You might think the patient has a metallic rod in their femur or something, but you notice when you do the flood there, it still exists, so a cracked collimator. And I'm sorry I rushed through those last few, but I was getting a little bit behind, a little more typical for me. And that concludes all the physics. Thanks, everyone, and I'll hang around a little bit if there are any questions.